Hi everybody, I'm Kate, I'm a designer, and I'm going to talk today about designing interfaces to connect humans and computers with the natural world. So for me, the kind of center of my work is this challenge of how do we, make this transition with machine and man feel very natural and feel good. And so the answer for a long time, or my answer, was to really make technology that's copying nature and copying our natural world. So I created all of these biomimetic wearable computers that merge man and machine for the imitation of nature. And this was like the center of my practice for probably like 5 or 6 years. And it was all about how can we kind of trick technology to feel natural and feel like magic. So this one was is a mating collar. When you get excited by someone, the collar actually flies based off the birds of paradise. This was a series of musical prosthetics, so similar to how kind of bugs and crickets rub their bodies together to make sound. These musical prosthetics were all hooked up with sensors, so they allowed you to rub your body together to make sound. And then I started to work with kind of how can we almost make natural technology in these unnatural spaces. So I started to work a lot with AI and how can we kind of evolve kind of nature in this in a technological way. So I started to do all these different GAN algorithms, so training these things. And so this project ended up with having kind of this stallion algorithm that was trained with moths and human eyes. So at the end of kind of this process, instead of having moths with fake eyes on their back, we had moths with human eyes on their back. And the cool thing about these moths that this algorithm generated is they actually trick surveillance cameras. So I'm always really interested in kind of that nature tech. This one will skip. But so that was kind of the center of my practice for a long time, was how do we copy nature to make technology. But then kind of one day I woke up and I was like, this is really gimmicky. I'm sick of copying nature. Why do I have to do this? And that's when I really started thinking if we want technology that feels relevant, so modeling the processes and kind of forms in nature and computational space and allowing to have these digital evolutions. And these came out, some of these algorithms came out with really exciting projects. The series is 5, I'm just going to show a few. But this one is a curved differential growth algorithm, so it's how meandering coral grows. And I really just started to explore with kind of these natural growth algorithms to see how we can merge kind of humans and technology. This one was a mushroom differential growth logic, so the same concept as the curved differential growth, only it's happening in 3D space. So this shoe was grown the same way that mushrooms are grown on trees and things. And the cool thing about this shoe is that it was 3D printed and it actually needed only supports where I made the hole for the foot. Everywhere else it grew completely on its own. So it was really interesting to see kind of what are the perks that some of these natural growth algorithms have for our physical manufacturing world. And then I started to really work with, okay, now we have these computationally generated forms. How can we start to pair that and make these things live and really make them alive? And so that started kind of the second phase of this idea of how do we grow technology. And I was working with living materials. So how can we work with materials that are still living, still moving, still changing? And so I kind of first started with materials I had. So I made this shirt that was made from wheatgrass, and what happened is I was able to grow it in mold and grow it kind of through this process where it actually allowed the roots to self-knit themselves together. And so all of a sudden we could grow these things that are all over the world and we can make them fully functional. So this was a root textile. And then I started to think, well, how can we have, not only the materials, but some of the processes and the materials in our kind of design manufacturing process be grown instead of manufactured. So I started working with bacteria to grow color to allow us to not only design in 3-dimensional space, but have kind of be able to take 2-dimensional designs from nature, which ended up in a lot of very beautiful swatches and scarves and all sorts of things. And then I started to really think, okay, so now we can kind of model these living processes, we can model, we can work with living materials, but how do we bring this back to technology? How can we make our technology more sustainable and living in itself? So I started to work with living interfaces and living electronic interfaces. And so this is kind of where my work is right now. This first project was working with slime mold, so slime mold is super cool. It can transmit electronic signals, and so what we started to do was really collaborate with slime mold to actually create replacements that are predictable and can be kind of trained to last a long time for circuit boards. So we started to grow all of these slime mold circuits, which was super cool and super fun. And this is kind of where my work's going now, is in this direction of, how can we do beyond just replacing solder with slimeable, but how can we actually unlock the computing power of living things themselves? So now I'm working with the Unconventional Computing Lab in the UK on mushroom computing and understanding how we can model kind of mushroom processes in our computing and really have that understanding. So that's neat. Thank you.
I'm Jack. Hi, friends. And today I'll be presenting material. As a person, I'm pretty materialistic. I'm technically obsessed with the things we can touch, fold, stretch, and hold. This is another taken to be my grace. And I'm so materialistic that I did a full degree in material science. I currently got it, also by that. And now I'm doing my PhD with CBA. And I consider myself to be a material designer. And the way to explain that distinction is through this definition of craft that I really love, which is craft is time spent in conversation with materials and the lessons they teach. And so material science characterizes how materials speak, and craft is the applied practice of this linguistic derivation. Digital fabrication acts as an interpreter between creative thoughts and physical creation, because the precision of machines provides a broad and precise language for these discussions from human to material to take place. So the first example of my explorations into this is my work Defense Tiles, which is a 3D printed fabric that arrived when I was thinking how to make almost anything. And I was undershooting and noticing these gaps forming. Thought it was a defect. But then I also thought, hey, wait, this is a useful way to program materials to be in lace or crushable or to make full garments of textile-like materials. And so it was me sitting with the machine having this material that allowed me to come up with all these different pockets or a 70-meter roll of fabric, which was printed in a single print over the course of a month and rolled out across the field. But I began to understand that machines really allow me to talk with materials in more rich ways. And then I began thinking, well, if I can talk or program materials in really rich ways, what should I do with them? And of course, like many people, I was inspired by nature, who's the master of craft and an alchemist of all materials. So the tree here, across the seasons, senses changes in its environment, it adapts itself, and it's only able to thrive because of its ability to do so. And so we need to free our materials from the comatose states we often subject them to, and give them a chance to adapt and persist against change. So then I began getting interested in active materials. This was a work that I did in my undergraduate on a artificial muscle fiber, which sounds familiar. And this can respond to heat, so we made a self-stirring tea bag, garments that can dynamically alter ventilation, and also a shirt that can give you a squeeze and give it a text message instead of an annoying vibration as a nice happy cue, but to bring this livingness into these surroundings. And then I even did a 4-line fashion collection in undergraduate called homeostasis, where we leveraged these polymer muscle fibers I developed to create active shape-changing garments, and then presented this at a fashion show at CMU. This was my final project for How to Make Almost Anything, where I moved from Pittsburgh to Boston. Boston's way sunnier. I was getting woken up by 7 a.m. by the sun, which I loved, but I hated the 7 a.m. part. So I created this sleep mask that goes from opaque to clear, so that I could wake up with the sun, but on my own time. And the really thoughtful part of this process was that it depended on the end-to-end integration between experimental materials and a finished product design. So the ability to do so depended on me holistically developing this. So I was moving between spaces, the wet lab versus the electronics room, and all of these factors were affecting each other. I would change how I did the material based on how I laser cut the molds. And so in my current and future work, I aim to use machine precision to breathe livingness into materials in as rich a way as possible. So the future of matter is systematically amorphous. These design materials will have vasculature, muscles, brains, and brawn. They can sense, compute, and respond to change, and thrive because of their ability to do so. And so in order to get here, we need to really break it down into two goals. The first is to be able to fabricate material systems. To do this, we need new machines, materials, and motivations to make this work happen. 1 minute. And then the second is to design material livingness. So much like in ideal human life, the material system should be carefully birthed through precision fabrication. It should live an actful and useful life through design and die an elegant death through biomaterials. And so all the time while we're doing this, we should be asking the question, is this material life? Is this just fantasy? Sentience and science are tied, no escape from physicality. Thank you.
Okay, good. Hi, I'm Tom. Nice to meet you. Do a grad program, started in 1979. We take people with basically with an undergraduate degree and a good story, and we give them an introduction to digital technologies in a hands-on way. That's Lolo. In case you're wondering, he's my workmate, or at least has been since 2020. Anyway, there's two projects that have sort of dominated my life over the course of my career. And with both of these, Arduino and physical computing, basically what I've been doing is helping to refine or complete the work that my partners started, which is something I enjoy doing, but in both projects I feel that really it belongs more to my partners than me. So it's time for a bit of a change. The one thing, though, that I think has been consistent throughout all my work is that a lot of what I do is essentially translating domain-specific language from various things to a broader audience, and that's something I hope to carry forward with me. My obsessions really are time and light. I've been thinking about light since my undergrad days. This was the first program I ever wrote back when I dropped out of computer science. I actually wrote this in the theater department. Computer science at Virginia Tech does not get credit for this. And so nowadays I'm really trying to think about how to make these two things the center of my work. In the spirit of this evening's theme, though, I'll try and talk about both time and light as material and process. So time as a material is an easy one if you're thinking about interaction design. In physical computing, we talk about time all the time because time plus action equals behavior, and that's something that we have to think about in physical interaction. This is a programming class at ITP, in case you were wondering. And really, one of the things I try to stress with people is you cannot interact with computers without a body, both yours and theirs. All computing is physical, period. I also talk a lot about this spectrum from automation to interaction. And basically, it's about that loop between us taking action and the machine taking action. And as that loop reaches the speed of human conversation, we call it interaction. As it gets longer, or as a time loop, then we think about it as automation. So I think this spectrum is kind of useful to talk about in class, and you can start to think about time as a material in this sense too. This is a project I did a while back, and it got me thinking about this idea that we all actually see time differently, particularly through emotions. This is a clock that checks my email, and every kilobyte that it receives is another 15 seconds on the clock. And then 2 years ago, I wrote both this one, which needs a little less explanation, I hope. Again, still thinking about emotional time. So again, we can think very much about time as material in these things. Light is also material, and particularly when we start to think about it in terms of its motion through time. One of the things I try to do in all my teaching about light is to get people not just to look at the light itself, but to really look at it as it changes over time, so that you can start to see the various things that happen in time. So it's both material and process in that regard. We can talk about the texture of light quite a bit. And backing up a stage there, in industrial settings, we tend to smooth that texture out. We just want illumination so we can do what we're going to do. The problem with that is it's really boring. The good news is that nature gives us texture and light quite well. One of the difficulties of this, of course, is that in a nerd setting, not unlike the one we may be in now, we often think, well, we can recreate this with projection, and to some degree we can. But there are two problems with that. First off, when we create it with projection, the minute we see anything with the projection frame, we think of it as something we should look at rather than something which should illuminate our lives. And second off, with projection, it's often difficult to get both the intensity and the warmth that we get from something like this, and those of us on the east side of the camp know this one pretty well, I think, at about 5 a.m. But we can explore temporal texture of light, the texture we get over time. Even the most boring spaces actually do have a texture as you watch them over time. And so one of the things I've been trying to do a lot of, thank you, is explore that. Moving on from there, though, one of the things I really encourage students to do is not to think about light as the topic, but as we're here to light the subject. So again, this lamp is not the feature, the cocktail is the feature, right? Our job as lighting designers is not to make you look at our work, it's to make them look at the thing you want to see. I do a lot of trying to get students to describe light because frankly most of us can't do it well. And it turns out to be an exercise they really enjoy doing. The more they think about the phenomena that they're seeing and just put it in simple words rather than think about concept, they start to be able to recreate it. And what's great is they come up with things I hadn't thought of. In this case, this is all about filters, not fixtures, which is really kind of a nice surprise. Sometimes they describe light on cats, of course, which is nice. And we did a project this semester around decorative features for emergency rooms. And a lot of my students went to the emergency room this year as a coincidence. But fortunately, when they were all there, they had the presence of mind to describe what they were feeling.
0 minutes.
Yep, thank you. That's going to make me skip over a few things. We can do a lot better with LEDs. This is me criticizing my own work here. And specifically, we can start to think about what happens when we use more than just RGB. Amber, lime, maroon, UV. We start to be able to get more of the color gamut. We can therefore create more colors. So thank you very much for your time. And I just want to finally say thank you to Haystack because I got to see the Big Dipper for the first time in 40 years the other night.
So it's me and Miana. We are together. So we're going to take 10 minutes.
Were they both on the agenda?
Sorry?
Were they both on the agenda?
Yes.
So that's
Yes.
solid.
Yeah.
So I'll go first. So who am I? I'm Patricia Stathatou. I'm a research scientist at the Center for Bits and Atoms. And my research and my work circulates around sustainability. And I'm trying to address global environmental challenges because I like to have this delusion that I'm somehow contributing to change the world or make it a better place. So I will talk to you tonight about two of my ongoing projects involving biomaterials, one for water purification and one for structural applications. So for water purification, I'm using yeast cells, or a yeast biomaterial, as I like to call it, in order to remove heavy metals at trace concentrations from water. And why heavy metals? Because these are very nasty chemicals, and once they enter the water bodies, they tend to stay there forever, and they bioaccumulate through food chains, and they pose serious threats to both human health and the environment. And the bad news are that conventional treatment methods fail to remove them effectively when their initial concentrations are low. So I have developed a biological process to do so. And here's an overview of what I did. So I cultivated yeast cells in the lab, and I harvest them in the peak of their exponential phase there. And after washing them several times with ultra pure water and lyophilize them, so they are in a limbo state, neither alive nor dead, they turn into this powder material that I then sprinkled in contaminated water. And after a certain contact time, I analyzed both the aqueous solution, but also the biomass using spectroscopic analysis and nanomechanical characterization. And I found out that the yeast cell wall plays a crucial role in actually binding with the heavy metals. So the yeast cell wall, as you can see here in this cartoon, is like a sandwich layered structure, fibrillar structure, and it has specific components that they like to bind with heavy metals. According to our analysis, these are like amide groups and carboxylic acid groups. Here's how the cell looks, and this is the cell wall. And this is the cell wall magnified before and after. So as you can see here, like heavy metals tend to create a thin film around the external part of the yeast cell wall. So that's how we clean water from heavy metals. And another project that I'm working on is how to use biocomposites, renewable source materials, for structural applications. So the Center for Bits and Atoms has a very long research arc in developing what we call metamaterials, which are architectural materials that exhibit exotic properties due to the interplay of the materials, but also the geometry of the structures. So the key thing about these metamaterials is that they are composed by lattices, which are composed by a Lego piece, a unit cell that we call a voxel. And previous students have made rigid, compliant, auxetic, which means that when you squeeze the voxel, instead of expanding in the perpendicular direction, it gets thinner. And chiral, which means that when you squeeze it, it twists. Voxels, that when you combine them together, you can make all sorts of structures that swim, fly, move, walk, jump. Here you can see some applications and collaborations that the group had in the past. But what I'm trying to do is currently make these voxel unit cells, instead of be made out of petroleum-based polymers and fibers, made out of sustainably or locally sourced bio-based polymers and fibers, but at the same time continue to exhibit these exotic properties, which is a challenge. And I have tried several combinations of bio-based polymers and fibers with no success because I couldn't outperform the petro-based materials until recently, where we started collaboration with a group in the University of Guelph in Canada, and they came up with a very interesting material for us, which is recycled carbon fibers coated with polyurethane and blended with a Sorona polymer. This is a polymer 35% coming from corn. And we are currently working on campus to injection mold them in-house and...
5 minutes.
Yeah, okay. And we aim to build houses out of them and compare it with 3D printed houses and traditionally built houses. So I'm heading up to Mayana.
So, hi everyone, I'm Yana Smith. I'm a grad student in Neil's group. I'm going to quickly talk about some of my research, and then we're going to talk about the work we're doing, the project we're working on here. So as Patricia explained, we want to make really large structures out of this kind of voxel feedstock, and if we want to do that, we need to be able to automate their assembly for this to happen at sort of any practical level. So in the past, CBA has taken this sort of swarm robotics approach to it, where you have many simple robots that are able to locomote over a lattice and manipulate individual voxels and place or remove material across the structure. So what I'm working on now is the next generation of this, in which the assemblers are able to not only assemble a structure, but also assemble themselves. So the basis of this is a functional voxel, or a voxel that is able to route power and electrical signal in addition to mechanical forces. So between voxels, we can route power ground information from these paths, and within an individual voxel, the face connections are here, and using these functional voxel faces, we can develop robotic modules to make assemblers. So in this case, this is a voxel gripper module that uses the voxel frame to route power to it as well as information, and is controlled using a 80 1624. And then using this kind of module, we can then stack them or assemble them in other configurations to create robotic assemblers. So this is the current hardware version, which is not running yet, but in software it is, like the simulation is. So in simulation, I've been working out methods of doing collaborative behavior between these robots because they're so simple. The addressable space, the sort of functions they can do is greatly assembled when they do coordinated behaviors. So this is looking at how we would pass a voxel stack, for example, between two of these 5-degree of freedom robots. This is looking at a version in which you can kind of on the fly reconfigure it to, in this case, expand its addressable space. This is the work that I'm trying to recreate in the real world. And then for our Haystack work, I'm going to pass it back to Patricia.
So why are we here? So as you all know, we are at Haystack, which is this amazing place that I guess that in order to get all the materials that are needed for this place to function, this involves like global supply chains, which are long, complex, and wasteful. So we are trying to see if we can make high performance, locally sourced, sustainable materials in order to make actually whatever we need in Haystack, or at least some of the parts that we need. And one of the things that we are making is superwood, the famous superwood. All of you have heard about it. So after chemically treating blocks of natural wood and removing the lignin out of it, we make the plant cells more compressible. And after heat pressing it with a very sophisticated hot press configuration that Ryan and Adeli invented yesterday, we were able to actually compress and densify the wood. And as you can see there, this is the before and after image. So we were able to compress it and decrease the thickness more than 70%. So we are very, very close to our target. And we will have more promising materials to show in the next days. And
another local resource coming out of fab labs or shops is the waste product from making things. So in this example, or in this project, we're looking at can we take a waste product like sawdust and transform it back into a material we can use. So we're looking at producing a lignocellulosic bioplastic, which is kind of like if we're taking sawdust and trying to reconstitute wood out of it. And if we're phrasing it as a question, can we make a useful bioplastic out of this? The answer is maybe. And then the next front that we're exploring is can we directly grow our own materials within reasonable timeframes? So this is looking at bacterial cellulose as an unwoven textile. So if we can use this in concert with some of the other materials to produce kind of like layup style composites. So this is grown in on kombucha, the pellicle itself, and then processed into a material form. So this is all in progress work, and hopefully by the end of the week we're going to have some really exciting results from this. Thanks for your time.
You just had it. Did I just have it? At the bottom.
Hi, everybody. I first want to thank everybody responsible for having this come together. Neil, thank you for getting all this equipment and people and stuff together. It's just been fantastic. I am blown away by all of the projects that have the unique privilege of seeing from my vantage point. My vantage point being that I'm an artist and an educator, and I've been a jeweler, traditional jeweler, and questioned many times what constitutes jewelry. So lots of questions about the materials, the structures, the behaviors, what they're for, what they're about. Lots of questions. These are older works from many years ago. This is The early work was more on structure. This work was really looking at the language of ornament and what it communicates, how it communicates. Is it a universal language? Is it a universal language with lots of different dialects? Things like that. So I'm very interested in that. That led me to another curious pastime that I had at the time. I was interested in 3D modeling with the Amiga computer. It was like this 1986 marvel. And I just found it compelling to be able to make these objects that were virtual. And it sort of, I used it like a sketchbook, just kept things going. However, as we all know, that was no longer a sketchbook anymore. It became a viable way of actually making physical things. Whether it was a powder material or it was a two wax material. And this was available in about 1999. So I'm talking about, for me it was available. It was available, I'm sure, at MIT and other places before that. But certainly it allowed me to make a series of work in, the turn of the century, 1999. That was, powder-based, 3D printed, coated with epoxy resin and enamel powder and stuff. And then the bottom was strictly they call it Sanders process, but it's a solid-state process. 2 waxes, 2 materials. And then but finished in the usual way. And this is, of course, this is the raw cellulose material that the 3D printer would print at the time. I still use powder-based processes for some things. This is a nylon, this is laser sintered nylon, this is a neck piece. But also you can see there's a holdover of the same kind of structure. I'm interested in the neck form. I like the repeating flexible neck object. It's one sculptural form that I think Brancusi missed, so I'm taking it over. This is an example of taking the 3D printed object into another level. It was a 3D printed object. It was molded in vulcanized rubber. It was cast in a low temperature bismuth alloy, tin and bismuth alloy. It was then electroformed over, dense silver plating. The bismuth alloy was melted out. It's a hollow silver form. So it's very strong, I've tossed them on the floor. I've lost them in the buffing wheel. They stand up. It's the same process that they use commercially for making things like baby rattles and other kinds of gifts like that. You can see that the bottom is a plug on the bottom for weeping out the material at the bottom. I got a little bit kind of confused about what I was doing, and I really thought that what I really wanted to do was get back to my hands at constructing things and not visualizing them and trying to go after that. And actually started making the components and parts that I could use sort of modularly with stainless steel wire to fit them together. And these are all 3D printed and then molded in the usual way, but entering into the usual workflow that a jeweler might engage in, filing, casting, finishing, etc. And using the computer for planning, for patterning. This is just hand processes, saw, soldering, all that stuff, but planning the process using the computer as a way of generating the idea. And getting interested in some things like some code. What is this pattern, this cracked pattern that I see? I didn't even know the term Voronoi at the time, and I started investigating it. And then on the far right, that's like a Visual Basic script. And this is another example of my foray into script. It's a Python script that takes a simple curve in Rhino, and then using the control points, it makes many copies of these just by jiggling the control points just a little bit, using a vector to move the control points here and there, just so that you can get as many of these varieties as you want. Sort of upsets the paradigm of designing in that you don't predict your form anymore, you choose your form. So I think it's kind of interesting. And I used that to make a 3D printed ceramic porcelain socket cups, which I use. I'm an educator. I primarily use my processes for teaching in the classroom, for using in the conventional way, jewelry, metalsmithing. These are some rings that I use as part of the demonstration process. I wore a couple of them the other day. Some student work. This is, I make a website for the students. They dump all their work in the thing, and so we look at it, and we all can look at people's processes and what they're doing. Things like this. This is an entry-level course where people are able to find out, figure out how to make things from the digital perspective, which they have not yet entered into. And it's kind of an exciting place. And, these kinds of things are really built into our process. It's just being able to plan things and make things on the computer and then allow yourself to make a tool that's a permanent roller printer. So, there's my soap dish, for my soap dish. It's a part of the demonstration, and thank you very much.
Hey, I'm Duarte. I'm an artist and I teach in the Department of Art at FSU. You'll have to pretend it's Monday because I'm going to show you artwork. The artwork that I make, essentially like all of my practices revolve around kind of the top half of this diagram by Arnold Pacey, which is like all of the kind of moral and ethical and political and cultural and human aspects of technology. But because I'm asking my audience to kind of cast a critical eye toward technology, it ends up that the work that I make often involves technology as material, as a medium. So one of the things I'm thinking about is, thinking about our relationship to technology and also how technology serves as a mediator in the ways in which we communicate with each other and our bodies communicate with each other and how our relationship to technology also. So this is, like back in the day, if you wanted to communicate with your friends and relatives who were back in the Matrix, you had to use the payphone at Haystack. And so this was here for like decades, and I assume decades. And when I came to the Open Studio residency in 2014, Stu, the director, said that it was going to be decommissioned, and so I bought a payphone and gutted it and replaced it with a computer and lots of wiring and scripts, and basically made this installation where you would sit in the payphone confessional and it would prompt you to tell stories or to listen to other people's stories. So you'd push the buttons and it would prompt you to do basically like stories about these superlatives, like your worst job ever, your best birthday ever, that kind of thing. So again, I'm thinking about our relationship to technology, and so I in thinking about that, I kind of in some ways approached it through a lot of projects in this kind of naive effort to understand maybe or to explain. And so I made this series of prototypes that are kind of absurd. They're drawing from like critical design, critical engineering, radical design, all these other things, Chindogu, things that are kind of like using this technique of absurdity as a foil. And so this is a prototype for a machine that inserts razor blades into apples. And here's a spread from a manual that I made that kind of imagined an industrial scale version of that. And a prototype for a machine that plays 5-finger fillet. A prototype for a machine that makes TV static, so you walk up to this and the lights would come on and the camera would come on and you'd turn the hand wheel and it would kind of slowly churn this bed of colored aquarium gravel, and through this whole analog video process it would kind of transmit that to another part of the gallery. And then I made these this series of machine performances, and they're kind of like really about this sensory experience, about space, and all these things that we're thinking about with sculpture, but they were machines that were doing all the work. So this one would blow up a balloon kind of like in breaths, like a person would over time, until the shadow hit the edge of that spotlight, and then it would burst. And then because it was overinflated, and then another one would kind of come up in this magazine of these turned brass shells, and it would start all over again. You saw that magazine was kind of like these patent drawings were in there, and so I worked with a group of architects to collaborate on this thing called the Institute of Patent Infringement, and we were looking at big tech patents, specifically Amazon, and I was making these patents that were kind of imagining this dystopic future of Amazon patents, and this was at the V&A in London and the New Institute in Rotterdam, and then finally at the Venice Biennale in the Dutch Pavilion. Then finally, I was thinking about like how technology maybe mediates the ways in which we read and write, and there's like this big history of that, electronic literature and electronic poetry and new media poetics, and so I had this this big stock ticker, and it kind of scrolls these 65 haikus that were kind of written in a computer-assisted way through Markov chains, and it was done by combining Marx and Engels' Communist Manifesto and Amazon's SEC filings from 2017. So it's kind of like the idea of haikus, taking these two disparate, contrasting subjects and putting them together, and also kind of the scrolling action. There were a lot of reasons why it was haiku, but it also was kind of like these really interesting and revealing texts that came out of it.
1 minute.
Okay. This is in that same line of thinking about electronic objects and text. It's kind of somewhere between like monument, obelisk, home appliance, and funerary item, and then it's welded and fabricated steel, and then it's got this tiny OLED screen that sort of ticks out this aleatoric poem that's generated from Google searches for the phrase "a man." So it's kind of like sometimes it's kind of like a eulogy or a celebration or an indictment. It's kind of like an interesting poem on its own, but it's totally attached to this object. So this is just the two of those in a show in North Carolina. And the last thing is the thing that I printed with Franco's help. I'm thinking about the pandemic and kind of the space between human bodies, and so maybe imagining what that negative space looks like. I'm using this process called generative design, so I'm literally just identifying where the fingers land in this case, and then kind of expressing the forces that they might exert by trying to reach for each other, and then having artificial intelligence come up with the actual form. That's that generative design process. This is a rendering of what it would look like in kind of matte black, and the idea is to have them be cast iron because you kind of have to hold them up by reaching for each other, and so as they get heavier, it kind of emphasizes that. And also, I'm imagining kind of doing, maybe that 6 foot distance. And here's the print of it. It's around. Thanks.
I'm Ryan Hoover. I'm an artist and educator and researcher. I have the benefit of working with Annette and Alan and Micah, with another great team of folks in the interdisciplinary sculpture department, which I'm currently chairing. We've recently added to our mission to center our pedagogy on care, which we think of as the working dimension of love. I think that notion kind of permeates a lot of the work that we do. So I want to talk about a few different projects and really focusing on this notion of collaboration. So I've done a lot of work as a woodworker. My father was a woodworker, and it's just kind of a go-to material for me. So I think of this as wood is like a bio-derived material. But from like this Bruce Hoadley book, which I think some folks here probably know, he reminds us that wood comes from trees. Whatever its sort of benefits or failings as a material for us as craftspeople, can all be traced back to that. So I started thinking about like how is it that this wood comes into being, and I took on this project of it's sort of a biomimetic project, but really looking not sort of from the top-down design, but really bottom-up. How does a tree grow, and trying to synthesize that, and really thinking a lot to try to criticize a lot of the notions of thinking about life and how that maps to computer programming, this kind of metaphor of DNA as code, and try to find the ways in which that's true and false. So with this algorithm, it can kind of grow like a kind of infinite variety of trees. But at the same time, this kind of object in the center, there's kind of two sides of this project. So here, I was actually working on trying to like 3D print wood. So we were like printing with plant cells, and we got that work, doing this work at the Baltimore Underground Science Base, a community biolab in Baltimore. And we were able to like successfully 3D print plant cells, and that was fun. There's a lot of other challenges to that. But some of the challenges that were really fun to work through were kind of designing some of the hardware, like keeping like hydrogel liquid without baking our cells. So we created this like little water jacket. Yeah. So also writing some weird software that been shared with other people who've used for a lot of other things like 3D printing clay or other fixtures. And also there's like weird like kind of high-res DLP stuff. Printed silk through like the How to Grow Almost Anything class. And worked a lot with this guy, Walter Zembeck. And we had this grant to work looking at how craft, it's a grant funded through the Center for Craft. So plants grow really slowly and mold grows really fast. So we kind of pivoted this project and decided to use cellulose from bacteria. So this is a couple different things. Like I'm pretty good at making things, like as a crafts person and with all these digital tools. Like I really suck at making anything at a nanoscale. These guys are really good at it though. So I think of them as our collaborators. We really co-load labor in making these objects. Typically they make this environment for themselves by creating this little mat that floats on water, so they live on top of it, so they have access to oxygen, but it's this really hygroscopic material that puts nutrients up to them. So they've kind of like engineered their own habitat. So this will happen like on Earth, usually in a flat plane. We created this aerosol bioreactor to fog it onto a surface, so we can grow it in three-dimensional forms. We did a bunch of post-processing things, like infiltrating it with water-curable resins, so we can machine it, made it into aerogels, embedded origami sort of fixtures in it so we can fold it to shapes, put kind of mechanical fixtures so we can make furniture with it. So the next project we were working on, like with biomaterials, this is really centered more on mica, was working with biocement. So we use this bacteria that can pull calcium ions, like dissolved calcium, out of suspension and grow these calcium carbonate crystals and stitch together grains of sand. So we kind of first started off with making something like about as impressive as you would find in your cat litter box. This is my cat reference for this problem. And a little bit better, and eventually get this like kind of sexy, shiny material out of this. That sounds terrible. We 3D printed this material with this super hacked Z-Corp machine, running all open source electronics. And a lot of this is done with students at MICA who are really awesome on this team. There's a researcher doing oyster habitat restoration who was looking for a new material. They currently use recycled oyster shells. And this is like a huge mountain of oyster shells until you think about the size of the Chesapeake Bay.
1 minute.
And that's like just not really going to make a dent in replacing the 99% of the oysters that we've lost. So we made some shells, tested those, they like it. This is more kind of like the structure we'll make ultimately. And this has led us into this project doing coral habitat restoration. So this is the design for our dome, it's a mold. And the goal is to make this carbon negative production unit that's deployable. So we're right now we casted a whole bunch of tiles. We made this kind of special pumping system to do this. This is what it looks like when we're running them. And currently we have a bunch of these samples sitting on a reef in the Florida Keys. And they will be tested for coral larvae on the new moon in a few days. So like our processes are tied to these like biocosmological connections. Sorry, this sounds terrible. So it's really this kind of like faster ecology of like scientists, bacteria, other organisms, and we're really working towards this kind of symbiotic approach, which I'd be very eager to talk with people about what this means in terms of like making with other organisms to kind of create a new design and sort of living perspective that goes along with all this. Thank you.
Neil's lab before I go to college next year. So I feel a little bit underqualified. Very lucky to be here, hanging out with all of you. So I'm going to talk a little bit about how I got here and what I'm working on. And so I started out by cold emailing. Oh, actually, no. First, this is another way I like to introduce myself. This is a minimum spanning tree of all of the articles I've read on Wikipedia over the last 2 years. It's very large. You can't see anything, but if you want to take a closer look at it, it's great. Come talk to me. I was going to try to find where Haystack and CVA were on this, but it's a little bit difficult, and searching it doesn't work super well, so you just kind of have to explore it organically. So I started out with the CVA by cold emailing Jake. Neil likes to put it as I emailed him and told him what he was doing wrong. I don't think it was that harsh, but I worked with him for a summer while I was in high school, and I was working on these tool changers, and I thought those were pretty neat. Tool changing is an interesting problem. I think we're still kind of working on it, but they liked me enough that they let me come back. But of course, there was the pandemic, so I worked at home, and I like to think I helped a bit in developing these blank tools that were eventually used to teach this, to teach the MTM class remotely. I worked on this 3D printer, which this architecture never quite made it anywhere, but you can kind of see the lineage of it in the clay 3D printer here. And so that was pretty fun. That's it. I guess it was frustrating to assemble, but I listened to the first book of Lord of the Rings on audiobook while doing this, so it took me that long. But it was cool. It was fun. Now I'm back. Actually, in between, I met Sam, who's a former student at Neil's lab, and I got to work with him earlier this year building wire building tools, which I don't have images of. But now I'm back at the CVA, and I'm building these little pick and place assemblers for modular microelectronics. So these are obviously not micro yet, spiraling in, as Neil likes to say. Honestly, my favorite part out of this is I learned the NASA standard for wire binding. So this is wire bind with Kevlar cable and to NASA spec, so that could go to space, I promise. So what am I doing here? I like origami a lot. I like origami a lot. I've been thinking about making origami machines for a while now. This is some sort of sketch that I did 2 years ago now of a roller feed origami machine. Drawing things by hand just to figure it out, and motivated by this. This is my favorite picture I've taken in origami. This is all the scales. Don't talk to me or my son ever again of hyperbolic paraboloids. This one's this big, this one's small, and I want to make them smaller, but then you have to start holding them with tweezers, and that sucks. So, you might have come by the graphic studio. So I'm taking Jake's clank machines, and he has a big wide format one, and there's a rotary tool. And you can actually see a very early version of this rotary tool all the way back there, from 3 years ago. And we're using that. We've made creasing and cutting tools to make this kind of cheap Zund replacement. It's kind of funny, actually. The tool I was working on with Sam was also a cheap Zund replacement, so I guess I should just really get myself a Zund. So they're very affordable in here. So I'm working on it. You might have come by the graphic studio and seen me screaming at JavaScript or making Jake fix JavaScript for me. This is my screen working. So there's clearly some work to do. It's a mess, but I thought it looked pretty neat of origami tools. And finally, this afternoon before dinner, it's working. So here's it applauding. The crease pattern for an origami crane on that high-speed paper. It's hard to take a picture of it. If you get the below angle light, you can see it crease there. It's a nice photo. So there's some more work to get to read SPGs, but come talk to me if you want to crease something, and I'm gonna make the cutting work, and it's pretty sweet. And yeah, that's what I'm working on here.
Should be minimized down there somewhere. It's not too. Theme is process and materials. So I'm going to talk about craft residency as process and system research. I'm a professor at the University of California, Santa Barbara. So I try to do research. Try driving convictions in some of the research I do that underline this talk. I think by understanding manual creators, we're going to develop impactful future technologies. And I also think that you can't make good tools for making without making good things, which is really frustrating as an assistant professor because I don't get to spend a lot of time making, so it's great to be here. The work that I do is done in the context of the Expressive Computation Lab, which is a lab that's almost 3 years old. I have a lot of great students who do really cool stuff in the lab, like programming languages, but you're programming entirely by drawing instead of by writing symbols. We look a lot at how artists are working to inform a lot of these tools, which I'll talk about more. Oh, sorry, this is work by Sonia Hishin, by the way, she's awesome. We also work on new materials. This is work by Mayor Hirsch. Actually, Mayor is now just graduated, doing rapid deposition sodium acetate crystallization, both as a fast form of additive fabrication, but also as a form of fabrication for performative applications, dance and music. Some of my students are also actively making artworks and sculptures. This is work by Samuel Igoe, looking at self-robotics as a medium for creating new forms and sculptures to inform the ways we might think about robotic work going forward. And then I also teach fabrication. Recently that's been less difficult because we've got to teach in person, but Nadia and I both taught digital fabrication and computational fabrication classes remotely, like many of you did, by sending 3D printers home to students. That was pretty challenging, but also there were bright spots, like students doing things at home, like an assignment where students have to write their own slicer, and a student made a flexible hammock for a baby turtle. So, not a cat, but so my research training is really structured around understanding how computation shapes different forms of making, and I'm really excited in finding ways to support different types of creators and using computation in powerful and productive and expressive forms. And I'm also really interested in domain-specific computational technologies in that space. So one of the things that we spend a lot of time doing is we are systems researchers. We build working interactive systems as a mechanism for exploring how specific ways computation can enable creators to integrate computational, physical, and manual creations. I spend a lot of time making programming languages or things like programming languages that also are a lot like drawing and failing productively each time. I also look a lot at then like what artists say about it when they work with these tools and how their experience in working with something like a programming language might compare to their experience working with a paintbrush, for example. The other thing I do is I spend a lot of time talking to people who are working in art and working in design and trying to get people who are working in the space of systems research to learn from all this rich knowledge in this community. So I look a lot at like how artists build their own software and how we might think about supporting software engineering in a way that looks more like the way artists work. And really important things come out of this that are arguably like not about software development, but more about what it means to make work using computational practices depending on your audience. So this is Molly Morin talking about how she makes sculptures that have an algorithm component. She has to explain to people what an algorithm is and why they should care about it, and that's a different market than more traditional forms of sculpture. Most of the work I do right now is centered around computational fabrication, which means a lot of things, but for me it means taking an algorithm, making a design, turning them into something that's useful and physical in the real world. A lot of steps in between. And one of the main areas I'm looking at is computational fabrication and craft. So both trying to understand about what knowledge from manual craft is absent in emerging technologies within the space of computational fabrication, and also how is computational fabrication relevant for contemporary manual craftspeople? This is hard to do because it's hard to understand a lot about what makes craft powerful. It's tacit. There are complex physical properties, manual skill. There's also complex cultural factors in a lot of craft forms. So the way we're currently approaching this, if you've talked to me, you've heard me talk about this because I'm stressed out about it, is by currently we're running a craft residency as a way to co-develop computational fabrication technologies. And also kind of tied to this idea is we're trying to investigate the opportunities of computational fabrication, not just for making craft objects, but for making craft objects you can sell with an existing craft market. This is a collaborative work in collaboration with Professor Leah Beakley, Emmanuel Montoya, Tim Castillo, and Ted Hojola. They're all at the University of Mexico. Cool. So builds on prior work I've done in this space, but I'll skip over that. And here's what we're doing so far. So we've brought in 4 residents from Contemporary Ceramics Craft Practice, all who sell their own work, who are going to be starting in a couple weeks in our labs. In the meantime, we've been building up our knowledge of computational ceramics productions by prototyping workflows in our lab, and also looking at how developing sample artifacts can help us to think about new primitives and processes for workflows that might be beneficial to other creators. And then in context with this, we've been interviewing master craftspeople. But I'd say like the main takeaways from this work for me have not been focusing on fabrication so far. They've been focusing on the challenges of actually running a residency in a research context. So lots of procedural challenges of what it means to run an art residency or craft residency in an engineering department. There's lots of process challenges, like how are we actually going to how do we select residents? How do we create robust methods for data collection? But the most important challenges we're running into are challenges around equity and reciprocity. What does it mean to ask professional creators to come in to share their practice and then use that to feed back into the engineering and research community? How do we make that equitable, and how do we evaluate our ability as responsible researchers to continue doing this work? So I'm looking at it as a process and really thinking about responsible collaborative research as a process that I'm trying to continue developing, and happy to talk about it more. Thank you.
Okay, another fabulous night. See you all at 9. Well done.
I love your work. So beautiful. So gorgeous.
I know, when you were saying the things about how artists work and that there's a language for building code with symbols, and my brain almost exploded. It's sort of what I've been thinking about forever, but not computation,
Yeah, well, we're, I don't know, I started in fine art and then moved more into...
Yeah. I saw a jewelry piece, right?
Yeah, that was one I did in Neil's class actually ages ago.
Look good.
I'm definitely going to show my students your work. We'd love to do stuff in jewelry. It's lovely to see it.
It's like
95%. Can I give you what is her name? We would show you how to use the software, which is and we do good work. So you would just like just add Haystack Labs, and then wake up the machine and make the materials happen.
So what
could you get her started tomorrow morning?
Think about this.
If not, I'll pair you something that will. Because we have.
Let's see who has.
my other professionals go on.
One patch to learn it or take it more.
I'm trying to think who has. That was last year, and Andre.
It wasn't last year, it was a year ago.
Yes,
And she's working with them to do that. So I think for like the past.
You know who I
Yeah.
Laura,
Yeah.
I think it's still just like.
the sewing part, Laura can help with.
Figure out so like in a lot of ways.
No, okay. But no, but it's actually really meaning, loading the thread and tensioning is actually the same. It's not just push it through the bell, but it's try to make it
but then there's the programming of the users that somebody that's done it before just needs to show you here's how you do it.
Once I
it's patched.
I'll ask to see the
Okay, well, I just find it is that not here, like I'm not a lab person here, and I like my other stuff getting done.
Yes, bound it, make it in, see how far you get from now on.
Okay.
And if it's not converging, hand off to somebody else to continue with it.
So, here we start out.
Start at the record.
We'll mention that.
Okay.
That's a good.
Okay,
That works.
good. Okay, anything we need to talk about? I don't think so. No. Okay, good. Let's see, Patricia and Ryan. I just put in the key. The read project. We're working on biomaterials, but one of the questions we're going to do is probably really not fabrication using our